Okay, so we are going to start with kinetic versus potential energy. The difference between those two, is that kind of what you wanted to know about that? So remember, your kinetic energy is going to deal with, that's going to be your movement of your molecules. So this is dependent wholly on what the temperature is of your compound. So the higher the temperature, that's going to provide more energy for your compounds and allow for more movement. So if we have higher temp, then that equals more kinetic energy, that equals more movement. So kinetic energy is the only thing that dictates molecule movement. That is a really big topic that AP likes to talk about a ton, is the relationship between those two. And every unit so far, I think we've talked about that. And in the spring, we'll keep talking about that relationship. In this unit, we see a little bit of an added topic of the idea that your mass can play a factor in this, a smidgen, because even though they have the same amount of energy, something that is lighter is going to be able to travel faster because it has less mass, but the same amount of energy. And so an example I've been using is the ping pong ball versus a bowling ball. Those have very different masses. If you were to throw them both, you have a certain amount of energy. You can only throw it with however well you can throw it. So if you tried to chuck those two across the room, the bowling ball is not going to go as far or as fast as your ping pong ball, because they have a different amount of energy. So the lower the mass, even though it has the same kinetic energy, it'll actually move faster as far as speed goes because it has less mass. If it has more mass, it'll go slower. And so that'll be like, you think about your ping pong ball versus your bowling ball. Kelsey, did you have a question?
So this is velocity for
Okay, so that's kinetic energy has to have some sort of temperature change involved in having that happen in order to be talking about kinetic energy. This unit, we talked a lot about phase changes. So that's going to come into play with our potential energy. So a potential energy, you're going to deal with a phase change. And so here we're going to be looking at how we'll have changes in our bonds. So you're going to be changing the number of this unit, since we're about intermolecular forces, that's what we're going to look at. It could also deal with intramolecular forces, but since that's more last unit, then we're not going to worry about that as much. So if you're changing your potential energy, you're not changing your temp. So you aren't going to be impacting your kinetic energy in any way. So when a solid changes to a liquid, it's going to stay stuck at that temperature until all of the solid changes to the liquid. So the liquid changes to the gas, it'll stay stuck at that temperature. So during a phase change, you're changing your number of bonds, strengthening them or weakening them, and you're not changing your temperature. So your movement of your molecules does not change. No, you're fine, sorry. So far, so good. So the next thing to think about, and that gets confusing for people sometimes, is when you're going to break intermolecular forces, which remember is going to be the same if they happen to be bonds. Remember the goal behind originally forming bonds in normal situations. When you have a bonded compound, that's going to be your lower energy configuration. So that's why your compound would form a bond in the first place, is to go to a low energy configuration. So when they bond, they're already at low energy configuration. If you go to break that bond, you're going to move them to a higher energy configuration. So unbonded is going to be the higher energy. So if you go from a bond to not being bonded, you break that, you're going to have to provide the energy that that atom needs to be unbonded. So breaking bonds is going to use energy. Let's say add energy. I like that better. So you have to add energy to break your intermolecular forces. So then when you're making your intermolecular forces, now you're going from an unbonded to the bonded. So you went from a high energy to a low energy, and so you're going to be releasing that energy. And so just a reminder that that energy that we're talking about is the potential energy. Sorry, I see you guys can't see me down there. Breaking intermolecular forces, you're adding potential energy. Making intermolecular forces, you're releasing potential energy.
Wait, so are you like increasing your potential energy if you're breaking intermolecular forces, or are you losing it because you're adding it to breaking bonds?
You are adding potential energy. You're increasing potential energy. Because we're talking about the energy within your atom.
Mm-hmm.
Here we're releasing the energy. Your atoms had the energy. When you make your bonds, they had to have them to be separate. And now when you move them to the low energy configuration, you can release that energy. So you're decreasing your potential energy. So let's be more. So this is going to increase potential energy. This one's going to decrease potential energy. Yes, sir.
So kinetic energy is not changed during phase changes, and then potential energy isn't changed, and it's just heating up and cooling down.
Perfect. So he said kinetic energy doesn't change during a phase change. And sorry, I think I pointed at the wrong one. So kinetic energy doesn't change during a phase change. Potential energy doesn't change when you're heating or cooling. Trying to recite what you said. Does that cover everything you wanted to know about that? Anybody have questions on this topic? So far, so good? Okay, then I'm going to move on to the next topic. I'm sorry, I only have so much space. I'm going to try to get a tripod so I can set up my iPad over there and use my whole smart board for the future. I just haven't had a chance to do that yet. So I'm going to erase this and we're going to talk about partial pressure for a minute. There's not a lot I want you to know about partial pressure for this test, other than just understanding the concept behind it. So partial pressure is the idea that the sum of your pressures are going to be equal to your total pressure. So if we have a box, and in this box we have different gases, so like I have my black dot and my purple dot, the sum of these two, whatever this pressure is, and this pressure is, they have to equal your total pressure. So when you do that, you can say this is going to be the partial pressure for black and the partial pressure for purple. Those two together have to equal your total pressure. So anytime we're saying partial pressure, it's just understanding you have multiple gases in the same place. And so you can look at those two values differently. And so relationship, somebody asked about how that relates to Pivnert. And one of the big things that kind of relates to is the fact that that N is going to be your number of moles. And when we're dealing with moles, the whole reason we use moles is because then it doesn't matter what element we're dealing with. It's always going to be about the number that we have. And since our number of moles is going to be the same, since it's all based on that Avogadro's number, then I can compare moles of oxygen just the same as moles of hydrogen. They would behave the same way. So number of moles of purple and number of moles of black are going to be the same. It doesn't matter what the substance is. So you could add your moles together and then plug that in for your Pivnert value and then solve for pressure. And that would tell you your total pressure. That would be, I think, one of the ways we used that here in some of our problems.
What if you're given 1 mole amount?
What if I'm given what?
What if you're given like 1 mole amount?
And only 1 mole amount
Mm-hmm.
and asked to do what?
It has to find like the total pressure or the pressure of the other gas.
We would have, okay, so if you were given that, so if I were given 1 mole amount, then I would plug that into Pivnert. I'm gonna make some assumptions. I don't know if you just made this question up, but so if we did that, I'd plug this into Pivnert and I would find out my partial pressure of that one. So let's say it's my purple dot, okay? So when I plug in my number of moles for my N, that'll tell me my pressure of purple, let's say, okay? So then once you know part of it, you're gonna have to make the assumption that if these are in a box, then the pressure that's pushing on the box has to be the same as the pressure pushing outside of the box. So you'd have to also be told some other piece of information, either what the total pressure is outright or the atmospheric pressure. And if you know the atmospheric pressure, you can assume that the total pressure is the same because that box has to be pushing out at the equal way that the outside is pushing it. So then you would know that's going to be equal to the atmospheric pressure. And so then now once you've figured out whatever partial pressure we had here, you would just subtract the partial pressure from your atmospheric pressure to know what's left. Does that make sense? I feel like that's as much as you would maybe need to know about partial pressures for now. Any other questions? You could add as many things as you want. You might have like 10 different pressures. In this room, we've got a lot of different gases happening. So the sum of all those pressures, there's not like a limit to how many you can add together. Yes, ma'am.
So you put in the partial pressure for it? Or would you just put both things?
It depends on the problem you're talking about. The one David just suggested is he said you were given a mole value for one of your pressures, and that's all you were told that in your atmospheric pressure. So you would plug in the partial pressure, or I'm sorry, excuse me. You plug in your moles amount for your moles, and then when you solve for your pressure, that would tell you the partial pressure for that substance, and then you would subtract it from your atmospheric pressure. Does that make sense? You could do it in reverse. If you plugged your pressure in, you would solve for the total number of moles. You would then subtract however many moles you had that were purple. You could do it both ways. Fair enough. Okay, I'm gonna say 4th hour was more interactive today than you guys are being right now, and that's like usually not the way it goes. So I need y'all to step up your game a little bit. What can I do to help you? Are we having questions? Are we being bored? Feeling okay? Okay. I think I'm having a hard time reading you all. Okay. So then let's talk about kinetic molecular theory, ideal versus real. This is an awesome time for questions. Like I said, it's always safe to be like, my friend has a question about this. Be brave. Questions are helpful, then I kind of know what direction you guys want to go. Yeah, we're going to talk about kinetic molecular theory and then how that relates to the ideal gases versus real gases, which is the first place we're going to overlap a little bit with 4th hour's video. Probably a lot. All right, so kinetic molecular theory actually has 5 points, but we're only talking about 4 of them. And so, hi.
Hi, do you know where Dr. Jensen's class is?
I think they are in 703, the computer lab downstairs.
Okay. Thank you.
You're welcome. So the 4 that you need to know for this test, there's the one we kind of talked about earlier, that the kinetic energy is going to be directly proportional to the temperature. which we've kind of talked about a lot, so I'm not going to talk any more about that particular one. And then the other one is the gases are in constant random motion. I'm not going to talk a ton about that one. It's the idea. That's how pressure is created from gases. Those molecules run into the side because they're constantly moving around in no particular direction. They run into a side, create a little bit of pressure every time they hit a wall. So we're able to measure that pressure. So weird. Then the next two we're going to spend more time talking about. We assume gases take up no volume. Sometimes it's said they're really far apart relative to their size. Very true. That's why it almost feels like gases are invisible or have no mass. Well, it's not actually true. That's an assumption that they made. And then the other one is that there are no attractive, gases don't attract or repel. Which we also know is not true. What? Kinetic molecular theory. Yes, this is the kinetic molecular theory.
And is that like what tells you when an ideal gas?
Exactly. Yes. So for our purposes, when we talk about an ideal gas, we're saying it follows all of those rules. And then the fifth rule we'll talk about second semester. So an ideal gas rule, this is going to be the guidelines for an ideal gas. Joey, do you have a question?
Yes, are you saying that the gas molecules don't attract each other, or just anything, or does it matter?
Yeah, anything. The idea is that they have no attractive or repulsive forces at all. For this unit, we're mostly going to be talking about how they attract and repel each other. So it's fine to think of it like that. Yes, ma'am.
Kind of off topic, but are we gonna have to know like Boyle's law, like that it goes with how
Pressure and volume relate? No, you don't have to name it. You should know the relationship between pressure and volume, which we did talk about during fourth hour.
Okay.
If you want to watch that, is like the first thing we talked about. So, and I can come back to it, of course. But all right, so let's talk about what makes the gas become ideal versus real. So there's a lot of situations. One of the common things that we're going to discuss is how a gas is going to deviate and situations that cause a gas to deviate. So that means to be like more real. So what we're looking at, especially since this unit's all about intermolecular forces, we're going to be looking at the strength of your molecules. Okay, so remember that if you have the strength, or let's say like this, strong IMFs are going to equal more deviation. Because we said they don't have any IMFs. So if you have, the more IMFs you have, the more you're going to deviate. So any situations that allow for IMFs cause more deviation. And so some examples of things that allow it to deviate would be, for example, if you have low temperatures. So if I have low temperatures, my molecules are moving more slowly, and I don't have the energy that the molecules need to overcome the intermolecular forces. So at low temperatures, there's not enough energy. I'm going to say no energy, but we know there's some. No energy to overcome your IMFs, which makes the IMF stronger, which leads to more deviation. So at low temperatures, you don't have enough energy to overcome those IMFs. That means break the IMFs between your molecules. And if you don't have that energy, that makes your intermolecular forces stronger. And remember, the more intermolecular forces you have, the more deviations you're going to get. Yes, ma'am.
I don't know if I did the connection, but is the ideal gas coincide in the molecular theory, or are they different?
They are the same theory. So these are the rules of your ideal gas law, or ideal gases. Okay, so that means more deviation means it's going to be basically like more real. It's a real gas. So anything you do that causes that is going to be the case. So we might not just change the temperature, you can also impact your pressure. So if we have high pressures, you have high pressures, that's going to allow your molecules to run into each other more often. And the more often your molecules collide, the more likely they are to react. Actually, our last kinetic molecular theory that we just haven't talked about a lot. But this creates more collisions. And so more collisions equal for stronger intermolecular force, which makes it more real. Think about your higher pressure. Like if you had a balloon, you're going to squeeze that balloon down. That's going to increase that pressure and push those gas molecules together because we know gases are really easy to compress. So when that happens, those increased collisions will allow your molecules to interact. And every time a molecule comes near each other, that's a likelihood that it's going to react. Or the more often it does, the more likely it's going to react. So low temperatures and high pressures mean you're more likely to have a real gas. So conversely, if you had high temperatures, then you would have the energy that you need to overcome those. So it's going to be more ideal. Low pressures, you're going to have less collisions, weaker intermolecular forces, more ideal. Be able to go back and forth between those two. There's one more that I want to talk about, but since you guys can't see down here, I was going to add it up here. Can I erase the kinetic molecular theories? And so one other thing that leads to things having stronger intermolecular forces would be the polarity of your compound. So remember things that are more polar. So if it's a polar compound, then that means it has at least a partial charge. And so if it has a partial charge, it's going to have greater Coulombic attractions. Just remember those Coulombic attractions talk about a positive and a negative being attracted to each other. So the stronger that charge is, whether it's partial or full or whatever, increases your Coulombic attractions. And the more Coulombic attractions you have, is going to allow your molecules to be stuck together. So that's going to cause stronger IMFs, which is going to lead to a real gas. So if it's polar, the more polar it is, that means the more charged it is, greater Coulombic attractions, stronger intermolecular forces, more like a real gas. And remember who asked about this. Does that cover kinetic molecular theory? Can you guys think of any questions that you read anywhere that you are curious about how this relates? The biggest place you're going to see molar mass effect would be two places. So the temperature change we talked about earlier, how we know the kinetic energy controls the movement of your molecules. And so if it's heavier, they're going to move slower. If it's lighter, it's going to move faster. So we kind of talked about that one earlier. The other difference would come into play with the concept of the difference, which is what we're going to talk about next, polarizability. So I'm going to erase this real quick and kind of switch gears. Hope that's okay. Should have probably asked. Good thing we're recording this. So if you remember, I've encouraged you to use those charts. So like if you have compound A versus compound B, and you go to fill it out, here you're going to talk about what the bond is, like ionic or covalent, so on and so forth. This unit's mostly going to be covalent. Then here you talk about, is it polar or nonpolar? And then here you would talk about your intermolecular forces. So here, if it's polar, it's most likely, it's for sure going to have dipole and London dispersion. Don't abbreviate on your FRQs, but I'm tired, so don't make me write a lot. And then it might have a hydrogen bond. What do we have to have in order to be a hydrogen bond? H and either F, O, or N. And remember, those have to be directly connected to each other. Can't just both be in the compound. Okay, versus London dispersion forces. So typically, these are partially charged, which means they're going to have higher Coulombic attractions on this side versus this side. So typically, London dispersion forces would lead you to having weaker intermolecular forces because they don't have a charge, so their Coulombic attractions aren't as great, typically. But then that's where polarizability comes into play. So if we have a compound that's very large, and there we're going to be talking about your radius more than we're talking about the molar mass, but you usually will be able to determine that by the molar mass because if it's heavier, it's going to be lower on the periodic table, so it has to have more orbitals. And so if you think about where the nucleus is, the bigger it gets, like you just noticed as I draw circles, see these electrons, it just naturally gets further and further away. And so as those electrons become slightly distorted or unevenly distributed, then your molecule becomes polar. Sound good? So the larger your atoms, or molecules, I guess in this instance, that's going to be more polarizable. And if they're more polarizable, that actually leads to the ability for those London dispersion forces to actually become stronger than these other ones. And so lots of instances we could use that.
So how do you know like when the London dispersion forces are stronger?
You would have to be given information. So if you were just asked to compare to with no background information, assume these are stronger than those.
Okay.
But it's a really common situation would be like I give you the vapor pressures or the boiling points, and you realize, oh, this one should have London dispersion, but it's stronger, so polarizability would be your use.
And they'll tell us that it's stronger.
Mm-hmm. They might not outright tell it. They might say this one has a higher boiling point than this one.
Okay.
And so then you would know, well, that one has the stronger bonds, so it must be more polarizable.
Okay.
You could have a very similar question that has this is the higher boiling point than this one, in which case you would talk about how those intermolecular forces are stronger because they have increased Coulombic attractions. So you just have to kind of read your data, what they really like to do. And on your FRQ for this test, you've got some data that you have to deduce which one's stronger based on what you're told. Definitely on the test. I don't remember if it's the FRQ or the multiple choice or both. What, as far as polarizability goes, does that, I don't remember now who's asked that question. Do we feel okay about polarizability? Do you want some practice with that one? Okay, then I'm going to move on. Do you have a question?
Does atomic radius affect polarizability or just mass?
No, atomic radius affects polarizability. That's what we're looking at.
So mass doesn't?
They go hand in hand. But it's because of the radius. Because of the radius, your electrons are further away. But if I've got a lot of electrons, I also have a lot of protons, so it's also going to have a large mass. So they go together. Usually we look for the mass just because it's an easier thing to think about, but it's because of the radius. So that takes us to trends, which relates really well to what we were just talking about. You guys want to talk about those? Okay. Any particular trends? Can I erase this? So anytime you're looking at your trends, draw your little chart, see the information that's been given to you. So like we were saying, boiling point is an example that we talked about. It's a good one to know. Boiling point and melting point are going to be the same. We'll have the same concept. So if you have stronger intermolecular forces, those molecules are going to hold together really tight. That means you're going to have a higher boiling point. So the stronger the intermolecular force, the more energy it takes to break it, the higher the boiling point, the harder it is to boil. More energy to break them apart, higher boiling point. So then you just have to think about, okay, so that tells me, comparing the two, which one has the stronger intermolecular force, you have to figure out the reason behind it. I feel like I'm boring you guys so much, and I feel really bad about it. I just want you to do. We okay? Okay, what other, do you just want to go through all the trends? Okay, vapor pressure would be the next big one. And so vapor pressure, remember, is that picture, it's terrible flats. You have your substance in here, and so vapor pressure is about what's happening up here. How much of your gas broke free of the liquid to become in the space up here. So you could measure that pressure. So if we're talking about being able to break free, the strength of your intermolecular forces is going to hold those molecules together. So if you have strong IMFs, you're going to have low vapor pressure because those molecules are going to stay together down here and they're not going to be released up here. So that means when you're looking for something that has a low vapor pressure, that's your clue that it has strong intermolecular forces. So when you're comparing those two, then you have to come up with some sort of reason why it has those strong intermolecular forces, like we talked about last time around. Volatility, same idea. Volatility is how likely it is to just evaporate, to break apart from each other. So volatility is about breaking apart. So the stronger your IMF, the more difficult it is to break apart. So you're going to have low volatility. Another one. Oh, surface tension. Bless you. And then surface tension is going to be how, like these molecules here on top, how tightly they hold together, how strong that surface tension is. So imagine you're trying to put your hand through the surface of something. And so if we're talking about intermolecular forces, the stronger the IMF, the higher your surface tension. Yeah, if you want to talk about viscosity, we for sure can do that. It's not on your test. But so viscosity is going to be the thickness of your substance. And so if you have strong intermolecular forces, it's going to be more viscous. You'll have higher viscosity.
What's the difference between viscosity and density?
It's kind of a density is going to be more of a mathematical measurement because you're talking about what's your mass based on your volume. And viscosity is more of like a qualitative way of describing a substance.
Yeah, viscosity, like how much it's like a gelatin, I guess. Okay.
Okay. What other things? So, I mean, this is just something you have to be comfortable with, so then you can explain it. Know that you can't just walk into the test tomorrow and have this memorized, but you have to like kind of understand how they all fit together. So understanding those strengths of the intermolecular forces is going to be what leads to this. So you get strong intermolecular forces when you have large coulombic attractions. And so that these things are examples or ways to tell how strong your intermolecular forces are, which is a way to tell how great your coulombic attractions are. So they kind of all go together. Okay. Then do you guys want to talk about STP? Some applications of STP? Can I erase this? All right, so STP is the idea of standard temperature and pressure. And so the concept there is it's just an easy way of using, so like people do an experiment or a situation if we're dealing with gases. If you would just do it at STP, then it's like more common conversation. So the temperature is going to be 0 degrees Celsius and your pressure is 1 atm. You can convert those into whatever variables you need to. But where that's going to apply the most in this unit is the fact that if you had 1 mole of your substance, the volume will be exactly 22.4 liters regardless of the compound. Remember, the nice thing about gases and dealing with moles is the fact that whatever your number of moles are, we're going to be dealing with the same thing regardless of what the compound is. So this is a relationship that we use a lot. And I think like that gas laws practice, you had like 10 different density type problems using STP. That's probably the most common one we used. Do you have a question? Okay. I can't off the top of my head think of compound examples, but we'll make one up that's a little similar to what we did before. So let's say you wanted to know the density of hydrogen gas. Okay, so hydrogen gas, you have to know it's diatomic, so it's going to be H2. And density, you have to know, which I think you're usually told, is going to be some sort of mass over volume. So a lot of times it's going to be grams per liter, could be grams per milliliter. You'll usually tell you what unit you wanted to. So given this information, I know hydrogen's molar mass is 2 grams. We have to remember that that's going to be 2 grams per mole. So that's the number of grams that you get for 1 mole. So if I need to get it to grams per liter, I've already got grams on the top. Now I need to have liters on the bottom, and I need to cancel out moles. So I need some sort of relationship between the two. And because this is a gas and not a solution, my relationship between moles and liters is 1 mole is equal to 22.4 liters. So I'm going to put 1 mole on the top, so my moles cancel, and then the 22.4 liter value on the bottom. And now I've got grams divided by liters, and I can go and solve this, and that would tell me my density of my substance. I think that's mostly how we used this unit.
So it always assume that the volume is 22.4 liters.
Well, because we're looking at the relationship between 1 mole and 22.4 liters, you would do that. There could be a situation where you might have to figure out maybe the molar mass based on that, and you would be told what the volume was, and that's the number you would start with. So like if I said there was, let's say 5 liters of some unknown gas, and you were given whatever its density is, you could put liters on the bottom and then be told your number of grams. Kind of use your density that way. I have to have a problem in front of me, but does that make sense? Because we're looking for the relationship between moles and liters. That's what we're looking at. That's pretty much where you would use STP, is just that conversion between 22.4. If there was one on your AFL that dealt with the fact that given 2 different containers, it doesn't have to be 22.4. If I had 2 volumes that were 11 liters, that's half of your normal volume. So you would assume you probably have half of a mole, but no matter what your substance is. The idea here is that's like proportionally always going to stay the same. So as long as you have the same volume, you'll be able to have the same number of moles.
And that's only an STP.
Yes.
So
The relationship will always be true for your volume and your number of moles. Like the proportional relationship will always be true, no matter what the temperature is. But to know what that volume is, you have to be at STP, because that's when we've calculated it out. Otherwise, if you're not at STP, that's when we would use PivNert and solve for it. And just for the record, if you ever forgot this number, you could always plug these things in to PivNert equation. That's how they figured out the volume. If you did the temperature, pressure, and number of moles, and you solve for volume, you'd get 22.4 liters based on PivNert. So if you had a different temperature, pressure, you just have to solve. You were asking me a question.
Is that related to the normal boiling point at all? No.
In what way?
I'm not, isn't it like at 1 ATM and like certain temperature too?
I want to say no. Probably not. I'm just not sure. No, probably not. Questions? Okay, then the last thing you guys have is polar and IMF. We talked about that yet? A little bit. I feel like we kind of talked about it, and now I don't remember what that meant. This relationship. So the more polar it is, the greater the charge it have, and so the stronger the Coulombic attractions. So polar typically is going to have those dipole-dipole forces. So maybe it would be worth, do we need to take a moment to remember how to figure out if something's polar or not polar? So if you were comparing two different compounds, let's say we had NCl3. In order to figure out whether it's polar or not polar, you have to draw your Lewis structures. And if we went to go figure this out, we draw all of our electrons. We put our electrons around the chlorines like we're supposed to make sure that chlorines get to their lowest energy configuration by all having 8. When we figure that out, that leaves us with 2 extra electrons here for nitrogen. So this would be the correct Lewis structure for NCl3. And so the shape that this is going to make, remember, is going to be trigonal pyramidal. So that causes there to be an imbalance. And so now we have to look at the difference between my nitrogen and my chlorine. Not a great example, because as far as fluorine goes, who's closer to fluorine, chlorine or nitrogen? Chlorine. So we're going to draw our arrows going down, although they're both pretty electronegative. It's not going to be hugely difference between the two, but our chlorine's going to be slightly more negative. Nitrogen's going to be slightly more positive because chlorine is closer to fluorine, which means trends, as far as trends go, it's more likely to be electronegative. And so if it's more electronegative, it has the electrons more often, causing it to be polar. So notice we have 2 poles. We have a positive pole and a negative pole. So that makes this a polar compound, albeit not super polar, but any form of polar allows for there to be greater attractions. So this is going to be a dipole force. What other intermolecular forces could it use? Can it do London dispersion? Definitely. Can it do hydrogen bonds? But it has nitrogen in it. It doesn't have hydrogen in it, so it can't do hydrogen.
So does it have to be polar to have hydrogen bonds?
Yes.
Okay.
That's a good question. It has to be polar to have hydrogen bonds.
So why can't it be London dispersion?
Because all molecules have the ability to interact with London dispersion forces, because London dispersion forces are just the ability to move those electrons. So any molecule can be London dispersion. Nonpolar can only be London dispersion. Polar also has dipole-dipole. Okay, we have 1 minute left, maybe. I think we feel good? Everybody's excited about taking a test tomorrow? Yay! Ah, you're all shaking your head.